All right, so we're starting this next unit on angles and lines. And within this unit, we will be learning some new theorems about angles and lines, but we will also be starting to do proofs. And this is actually a question that was asked of a writer, Marilyn Beausavant, and she has a high IQ and she does lots of puzzles in the Parade magazine. I don't know if you've ever read that, but this is her response to someone asking her, when in our lives are we going to use proofs? So you're welcome to pause the video and read that. So we're going to start with reasoning with the properties from algebra. And we're going to do this because algebra is something that we're used to. We already have a mechanism for the procedures that happen with solving algebraic equations. So it's a gentle way to start proofs. And I'm going to remind you about some of the things that we know about algebra. These properties will need to go on your proof cards because we will be using them in proofs. Okay, so the first one is the addition property of equality. And that says that if we have two numbers, a equals b, or anything equal on each side, then I can have a plus c equals b plus c. Notice that all we did was add the same thing on both sides of the equation. All right, so we've done that before, right? You've done that all the time when you're solving equations. And then we have the subtraction property, so that's going to be very similar to the addition property, except now we're going to subtract c on both sides. And then the multiplication property, what do you think that will do? We are going to be multiplying by c on both sides. So AC would equal BC. And then on the division property, the only thing that changes here is we can't have c equal 0 because we're going to be dividing by c. So I can divide both sides of the equations by c, as long as c is not a number that's 0. So those are things that you've done a million times before solving equations. You do the opposite thing on both sides of the equation. All right, so reminder of those. The next one, the reflexive property of the equation. This may seem obvious, but we'll be using it from time to time in our proofs. The reflexive property says if you just have any real number, okay, it doesn't matter what that is, then A is equal to A. All right, so I know that's just like, why would we ever need that? But sometimes we'll need to show that something is equal to itself. All right, so symmetric property says if I have A equals B, then I could also write B equals A. It doesn't matter which side of the equal sign it is on. Okay, so reflexive, it looks like it's looking in the mirror, so A equals A. All right, but symmetric means it's symmetrical. I can have A equals B or B equals A, can flip around either way. And then the transitive property, notice that this one starts with two equations. If A equals B and B equals C, then we know that A equals C. So you see how in both equations that it's equal to the same thing. Two things are equal to the same thing. So in this situation, it's B. So then we know those two things are equal to each other. It's almost like the equal property for like law of syllogism that we did in the logic unit. Okay, and then we have the substitution property. So if A equals B, if those two things are equivalent, then A can be substituted for B. And here's how that might look in any equation. So for example, if I have A equals B, and I have something like B plus C equals 1, well then I could also write A plus C equals 1, right? Because these two things are equal. All right, so I substituted, I replaced A for B in an equation. Okay, so that's the substitution property. And then distributive property, this looks a little different. Here we don't have to start with an equation. It's just an expression. It could be done in an expression or it could be done within an equation. But if we have A times B plus C, then we can distribute that to equal A times B plus A times C. Okay, same thing with, it can go backwards too. right? So I think you know the distributive property, just know that whenever you do that you can use that as a reason for why you're doing that. Okay, so all of those are properties, and those are going to be reasons that we use to justify how we know something. So let me show you how we're going to use these properties. Oh, before we do that, let's look at just some more versions of the reflexive property, the symmetric property, and the transitive property. This is because these are the newer properties, so it might help you to see. You can do it with real numbers. So like the reflexive property, you could have A equals A, so you could have like 15 equals 15. But you could also have it with segment length. So you could say, okay, the length of AB is equal to the length of AB, or you could have measures of angles. The measure of angle A equals the measure of angle A. And that's really what we're going to use it more so for in our geometry proofs, are those segment lengths and angle measures. And then symmetric property can also be used with segment lengths and the angle measures. So if I have this, then I can rewrite it like that. It doesn't matter which way I write it on the equal sign. Same thing with angle measures. And you don't have to rewrite this down. It's just another way of seeing that property in action. And then the transitive property, we will use that quite a bit in geometry. So here's an example: if AB equals CD and CD equals EF, notice that I have the CD repeated, so that means AB equals EF. That's the transitive property. And that was using it for segment lengths. And that can also be used for angle lengths or angle measures as well. So if the measure of A equals the measure of angle B, and the measure of angle B equals the measure of angle C, you can see that measure of angle B is repeated, so we can say A and C are equal to each other. All right, so let's look at how we're going to do this. Notice in the directions it says solve the equation, write a reason for each step. So we're going to do this in a more structured way. We're going to do what we call a two-column proof. So I'm going to keep all of my statements on the left, and this is just a way to organize our work, and then the reasons on the right. And we're always going to start with what was given. So what was given? We were given just this equation. So how do we know all this stuff is equal to 8x? Well, because they told us. So whenever, that's the reason you write given. Okay, so that should always be your first step, is writing the given. So our next step, if we were trying to solve this equation, then we would distribute, right? So we would rewrite this equation like this: 12x, and we would distribute that negative 3, so that would be minus 3x minus 21. So the reason we can write this statement is because of the distributive property. So that's just illustrating the distributive property. And you will notice that I will start abbreviating because we'll start writing a lot of properties. So just be aware of that. The next thing we would do is combine like terms, right? It's 12x minus 3x. We did not write this, but this is just called simplifying. I would also accept combining like terms. This is not the addition property or subtraction property, because subtraction property subtracts things on both sides of the equations. All we did was combine like terms on one side. Okay, and then the next thing we would do would be to subtract the 9x, get the x's on one side. Okay, so you don't have to show that minus 9x on both sides, but what we would end up with is minus 20 or negative 21 equals a negative 1x. So we can say that because now this is the subtraction property. We subtracted 9x on both sides. So subtraction. And I'm going to write POE, that's abbreviation for property of equality. So I can do POE when I'm doing something on both sides of the equation. And then our next step would be to divide by the negative 1, right? And again, you don't have to show that you're dividing by the negative 1. All you have to write in statement 5 is that positive 21 is equal to x. And that's the division property of equality. Okay, so then we have solved for x, so x is equal to 21. If you wanted to, you could write it like this for your sixth line. And what would that be called? That's the symmetric property. Because all we did was switch which side it was on. Okay, so we just completed our first algebraic proof, and you can see that we already know the steps for solving, and all we have to do is list the reasons each time. All right, so what I'd like for you to do is try this, number 2, try setting that up on your own. Pause the video, try setting it up on your own, and then I'll show you what mine looks like. So take a look at my proof. So hopefully you did your statements and your reasons and you started with the given. Pretty much the next step really needs to be distributive property. And again, for number 3, you could have done simplifying. The reason could have been simplifying or combining like terms. Some people, though, I know you would rather just subtract 4 and then subtract 10. So that's okay to do as well. That just makes it a little bit longer. You can also do steps 4 and 5 in opposite order, but your last step really needs to be the division property because you have to get rid of that coefficient in front of the x. So there's a little bit of room for different steps in the middle, but the beginning and the end should really be the same. So if you have questions about that, then ask me about that in class. All right, let's do one more, but this time we're going to do something more geometric. Okay, so we have a diagram, and in the diagram it tells us that AB equals CD, and notice that they marked them with those congruent tick marks, and we're trying to show that AC is equal to BD. So that whole segment, you see how they marked it in blue. When you're given a geometric diagram, what's mostly important is you want to figure out why that even makes sense. The thing about algebraic proofs, they're easier because we already have a procedure, steps that we already know. With geometry, we don't know the steps in advance. So each time you get a diagram, you have to figure out, why does this make sense? How am I going to get there? So it helps to just think it out first before you start writing your statements and your reasons. Okay, so if we look at this, why would this distance be the same as this distance? Well, if we think about it, they both have this segment in the middle, BC. So we don't know what it is, but we know it's the same for both of them. And then they also have these AB and CD. Those are also the same. So they're made up of 2 different segments that are the same lengths. So it would make sense that the total lengths would be the same. So if we see that 2 segments make up the total, then that's going to be going back to the when we did a few units ago, that segment addition property. Okay, so think about that. And that's why I have you do those proof cards. You can go back and look at your old proof cards and find that card that says segment addition property. Okay, so let's talk about how we would write up this proof. All right, we always start with what we're given. So we're given AB equals CD. So our reason for that one, I'm going to label these. That's 1. So our reason is simply given. And then for the second one, this is where they're saying AC, that one is made up of this segment AB and this segment BC. Okay, so that's that segment addition. I'm going to put, instead of addition, I'm going to put plus. And instead of postulate, I'm going to write post. Okay, so that's how we know that AC is equal to AB plus BC. AB plus BC, yes. Because that's the segment addition postulate. That's exactly what it says. Okay, and then the third line says that BD, that's this one, is made up of BC and CD. Okay, so again, that's the segment addition postulate. Okay, so 2 and 3 were both for the same reason. Some people like to combine 2 and 3 into one single, and then they can just have one reason if it's the same one, and I'm totally okay with that. All right, so here's what they're doing now. They're saying AB plus BC equals CD plus BC. And notice that they put in red that they were adding the same thing. So really what they're doing is taking this original given statement and adding the same thing to both sides. So what do we call that? That's the addition property of equality. So why would they choose to do that? Well, the reason they did that is because they noticed that these both had a plus BC in them. So if they start with the original and then do the plus BC, then these are going to match what these two things are equal. Okay, so then now they have, in our last statement, they have what we were trying to show. We were trying to show that AC equals BD. And the reason they can write that now is because AB plus BC, we said that was equivalent to AC. So they replaced it. And then the same thing over here, CD plus BC, we said that was the same as BD. So that's why we can replace that. So what do we call that replacement? That's substitution. So all we did was substitute equal things. So again, like I said, if you have questions about this, please ask about it in class.